A complete plant or production machine mostly consists of different technological parts, which can be separated from each other. For the technologist, a machine for labeling cups, for example, consists of the material feed, a labeling unit, and the packing unit. The automation designer can subdivide each technological unit into further independent subtasks, such as conveyor belts, lifting units, etc. If functional units can be identified, which can be used jointly by several technological units, this is referred to as a structured approach. In this example, this could, amongst many others, be a motor control, valve control, failure display, or part load count. This form of structuring is the basis for simple solutions to complex tasks. Step 7 supports you in this task with its programming and block concept. A Step 7 block is a part of the user program separated by function, structure and purpose, which enables structuring extensive and complex control tasks. As a user, you have the advantage of easier programming due to smaller functions, better overview over the entire plant, easier testing and commissioning of your plant as each component can be dealt with individually, and the possibility of reusing a once realized functionality by generating libraries. Let us take a closer look at an example taken from a possible realization of this plant structure. In principle, an entire program can be, instruction by instruction, contained in one single block, for example the organization block OB1. This is referred to as a linear program. This type of programming, however, has the disadvantage of not being clear, hence prone to errors, huge programming requirements, and increased memory requirements. The Step 7 block concept is predestined for the structured realization of this task. For processing the blocks, which control a technological or functional unit, they are called successively or stacked in an organization block. After they have been processed, the program automatically jumps back to the return address in the calling block. Step 7 offers you different block types for encapsulation of your subtasks depending on the application. As shown in the preceding section on the execution system, the organization blocks are the interface between the operating system and the user program. The main program is generally located in the cyclically called OB1. For example, OB1 calls the technological unit of the first conveyor belt. This subtask has been realized as function block, FB for short. A function block can be parameterized flexibly and has its own memory in form of an instance data block. This data block, DB for short, is created by the program editor in an instance on first calling the FB and is primarily only available for this FB for data exchange. The result of calculation and logic operation of a function block can therefore be dependent on the status of the current call parameter and on the status of stored data from earlier cycles. In a function block, further blocks can be called. An example is the task of displaying and processing error signals with a reusable function. A function, or FC, is used for programming frequently recurring automation functions. It can be parameterized and can return an optional return value to the calling block. Functions generally do not store any internal information beyond their runtime. They only communicate via their input and output parameters. System functions, or SFCs, are parameterizable functions integrated in the operating system of the CPU, whose number and functionality are fixed. In this example, the current system time can be read from the operating system of the CPU via an SFC. Similar to the function blocks, there are also parameterizable system function blocks, or SFBs, integrated in the operating system. which on being called only need to be supplied with an instance data block. Structured and type-coded user data can be stored in data blocks. There are two ways of realizing the application of data blocks. As a global data block, which can be used as free data block by all other function-related blocks, and as instance data block, which is always assigned to a function block and only contains the local data of this block call. After the program of the first conveyor belt has been processed completely, all further plant parts intended for execution are successively called in OB1. Identical plant components, such as a further identical conveyor belt, can now be processed by simply calling the same block with other I/O parameters and a separate instance DB. This way of creating the user program illustrates how simply, clearly displayed, execution and memory optimized, reusable programs generated in the same or in different projects can be generated with blocks. A simple user program is used to illustrate how a function block communicates with the various memory areas of the CPU via its parameter interface. The ladder diagram displayed here implements a simple multi-usable motor block. The motor is switched on and off via push button. The on status is additionally displayed via a blinking signal. The block can be used repeatedly for the same motor type. A certain motor is selected merely by assigning the interface. The program of the block, its function, remains unchanged. The inputs are addressable via the memory area of the process image and are connected with the input parameters of our block. A program-wide uniform enable signal for all motors is located in a global data block and is also connected to the input parameter. The central blinking signal is automatically assigned to a global memory bit via parameterization by the CPU, and it is connected to a further input parameter. The controlled motor contactor and the blinking light are connected with the address in the process image of the outputs via the output parameters. The status of the storage element in the program must also be maintained after terminating the motor block. A static variable is therefore created in the declaration section of the FB. For an FB, all parameters, temporary and static variables, are stored in the instance data block. The operands of the user program used in the block are exclusively switched via the symbolic name of the block parameter and static variables of the declaration section of this block. The functionality is now completely encapsulated. Physically, the block exists only once in the memory of the CPU. However, it can be called up in the program many times using an instance DB.